Picture this: a star, millions of times brighter than our sun, collapsing under its own weight in a final, violent explosion. For a fleeting moment, it outshines entire galaxies, unleashing energy so immense it bends the very fabric of space and time. This is a supernova, one of the universe's most breathtaking displays of raw power. But what if I told you it's just one of countless forces shaping the cosmos, each more mysterious and magnificent than the last? The universe is a stage where titanic energies dance in the dark, black holes devouring stars, invisible dark matter weaving galaxies together, and magnetic fields strong enough to tear atoms apart. These aren't just abstract ideas from a physics textbook. They're the invisible hands sculpting everything we see, from the tiniest particle to the grandest galaxy. And today, we're about to uncover 30 of the most astonishing forces driving this cosmic spectacle. Think of it like this: every second, unseen battles rage across the cosmos. Gravity pulls, radiation pushes, and matter transforms in ways that defy imagination. Some of these forces are so colossal they could rip planets apart in an instant, while others work silently over eons, stitching the universe together one atom at a time. What ties them all together? They're the architects of reality itself, and understanding them is like peering behind the curtain of existence, so buckle up. We're diving deep into the heart of these celestial mysteries, where the rules of physics twist and the ordinary becomes extraordinary, ready to explore. Let's begin. At the heart of our galaxy lies a monster, a gravitational abyss so powerful that not even light can escape its grasp. This is Sagittarius, a star, the supermassive black hole anchoring the Milky Way, with a mass 4 million times that of our Sun. But what makes black holes so terrifyingly unique? It's not just their appetite for destruction, it's the way they rewrite the rules of physics. Picture spacetime as a stretched rubber sheet. Most objects, like stars or planets, create gentle dips in the fabric, but a black hole, it's like dropping a cannonball onto that sheet, tearing a hole so deep that anything crossing the edge, the event horizon, plunges into oblivion. Time itself slows to a crawl near this boundary, as if the universe hesitates at the point of no return. And while we often think of black holes as cosmic vacuum cleaners, they're more like whirlpools. Cygnus X1, the first black hole ever discovered, spins so fast it drags the very fabric of space around it, twisting reality into a vortex. Then there's Hawking radiation, the ghostly whisper that hints at black holes' mortality. Quantum mechanics suggests pairs of particles flicker in and out of existence at the edge of the event horizon. Occasionally, one escapes, stealing a tiny bit of the black hole's energy. Over trillions of years, this slow leak could cause even the mightiest black hole to evaporate. It's a paradox. These cosmic titans, seemingly eternal, might ultimately fade away like smoke. What's truly mind-bending is how black holes warp our understanding of existence. They're not just objects in space, they're places where space and time cease to behave as we know them. A clock falling toward a black hole would tick infinitely slow from an outsider's perspective, while someone unlucky enough to cross the event horizon would be stretched into spaghetti by tidal forces long before reaching the singularity, a point of infinite density where physics itself breaks down. Yet without black holes, galaxies might never have formed. Their gravity sculpts the cosmos, pulling stars into orbits and seeding the universe with heavy elements when they collide. They're destroyers and creators, chaos and order, all wrapped in darkness. Now imagine a star's final act, not with a whimper but a cataclysmic roar. When a massive star exhausts its nuclear fuel, gravity wins the battle it's been fighting for millions of years. In less than a second, the core collapses, triggering an explosion so violent it can briefly outshine 10 billion suns. This is a supernova, nature's ultimate fireworks display, and the universe's most efficient alchemist. Take the Crab Nebula, the remnants of a star that exploded in the year 1054. Chinese astronomers recorded it as a guest star, so bright it was visible in broad daylight for weeks. That single event released more energy than our Sun will produce in its entire 10 billion-year lifetime. But supernovas aren't just spectacular light shows, they're cosmic forges. The extreme heat and pressure in those explosive moments fuse atoms into elements like gold, platinum, and uranium, scattering them across space. Every piece of jewelry, every smartphone circuit board contains atoms forged in these stellar explosions. What's truly humbling is realizing we're made of stardust too. The oxygen we breathe, the calcium in our bones, even the iron in our blood, all were cooked inside stars and hurled into space by supernovas billions of years ago. Without these explosions, the periodic table would stop at iron, and life as we know it couldn't exist. Modern astronomy has revealed even wilder varieties, like hypernovas, supernovas on steroids, where a rapidly spinning star collapses into a black hole, firing jets of gamma rays at nearly light speed. One such event, 2006's JAB 060429, released in 20 seconds what our Sun would take 15 trillion years to emit. And then there's supernova 2006 GY, the brightest ever recorded, which at its peak was 100 times more luminous than a typical supernova, challenging everything we thought we knew about stellar deaths. These explosions also serve as cosmic measuring tapes, because certain supernovas always explode with the same intrinsic brightness. Astronomers use them like lighthouse beacons to map the expansion of the universe, a technique that revealed the shocking discovery of dark energy. From creating the building blocks of planets to helping us measure cosmic history, supernovas remind us that destruction and creation are two sides of the same celestial coin. The next time you look up at the night sky, remember those dark spaces between stars aren't empty. They're littered with the remains of explosions that made our existence possible. When a massive star explodes as a supernova but doesn't quite collapse into a black hole, something even stranger remains: a neutron star. Imagine crushing the entire mass of our Sun into a sphere barely the size of Manhattan. That's the incomprehensible density of these cosmic leftovers, where matter is squeezed so tightly that a single teaspoonful would weigh 1 billion tons on Earth. It's as if all the cars, skyscrapers, and mountains on our planet were compacted into a sugar cube. What creates this extreme state? During a supernova, the star's core collapses with such force that protons and electrons merge, forming a sea of neutrons. The result is a star made almost entirely of neutrons, packed shoulder to shoulder like sardines in a tin. But neutron stars aren't just bizarrely dense, they're also cosmic powerhouses. Some spin hundreds of times per second, flashing beams of radiation like interstellar lighthouses. We call these pulsars, and they're some of the most precise clocks in the universe. The Crab pulsar, born from that legendary supernova in 1054, rotates 30 times every second, emitting radio waves with such regularity that astronomers initially mistook them for artificial signals from an alien civilization. Then there's the neutron star's terrifying cousin, the magnetar. These objects possess magnetic fields a quadrillion times stronger than Earth's, so intense they could wipe credit cards clean from halfway across the solar system. In 2004, a magnetar 50,000 light-years away unleashed a burst of energy that briefly compressed Earth's upper atmosphere, despite being farther than most stars we see at night. If one happened within 10 light-years of us, it could strip our planet's ozone layer, triggering mass extinctions. But perhaps the most jaw-dropping neutron star phenomenon occurs when two of them collide. In 2017, gravitational wave detectors picked up ripples in spacetime from such a collision 130 million light-years away. As the stars spiraled together, they ejected gold and platinum in quantities exceeding Earth's entire reserves, creating in seconds what our planet took billions of years to accumulate. These cosmic crashes are nature's ultimate jewelry workshops, proving that even in destruction, the universe crafts beauty. Neutron stars challenge everything we know about matter. Their gravity is so strong that their surfaces may be crusts of iron atoms stretched into spaghetti-like strands, floating atop a quantum soup of neutrons. Some theories suggest their cores might contain exotic states of matter, quark, gluon, plasma, or even stranger materials that defy our current physics. They're cosmic laboratories for conditions we could never replicate on Earth, pushing the boundaries of what's possible. From their birth in stellar explosions to their role as galactic alchemists, neutron stars remind us that the universe's most extreme objects often hold the keys to its greatest mysteries. Hidden in the darkness of space, a single event can unleash more energy in seconds than our sun will produce in its entire lifetime. Gamma-ray bursts are the universe's ultimate cosmic fireworks, brief, violent eruptions of high-energy radiation so intense they can outshine every star in their host galaxy combined. And if one happened nearby, it could erase life across entire solar systems without warning. These terrifying bursts come in two flavors, each with its own catastrophic origin story. The short bursts, lasting less than 2 seconds, typically occur when two neutron stars spiral together in a deadly dance. As these ultra-dense corpses collide, they create jets of radiation moving at 99.9% the speed of light, particle accelerators on a cosmic scale. The long bursts, lasting minutes, stem from hypernovas, the collapse of supermassive stars into black holes. Unlike ordinary supernovas, hypernovas don't explode symmetrically. They fire focused beams of annihilation from their poles like interstellar blowtorches. The most chilling proof of their power came in December 2004, when a gamma ray burst from a magnetar 50,000 light-years away. Inside our own galaxy struck Earth's atmosphere. For 500 milliseconds, this burst of energy outshone the full moon, despite originating near the constellation Sagittarius. It compressed our planet's ionosphere, triggering the first ever observed disturbance in Earth's magnetic field from a cosmic explosion. If that magnetar had been just 1/10 the distance, the resulting radiation could have triggered a mass extinction. What makes these events truly humbling is their staggering frequency. Satellite observations suggest gamma-ray bursts occur somewhere in the observable universe roughly once per day. Most are so distant their light has traveled billions of years before reaching us, their host galaxies long since transformed by cosmic time. Yet their afterglows, lingering X-ray and visible light emissions allow astronomers to pinpoint their origins with precision. One burst, GRB 090429b, holds the record as the most distant single object ever observed. Its light began traveling toward us when the universe was just 600 million years old, a mere infant by cosmic standards. These explosions serve as time capsules, their radiation carrying clues about the early universe's composition. But they also pose an existential puzzle. Could a nearby gamma-ray burst have already sterilized promising planets in our galactic neighborhood? Some scientists speculate such an event might explain the Fermi paradox, the eerie silence in our search for extraterrestrial intelligence. For all their destructive potential, gamma-ray bursts also play a creative role in the cosmos. Their intense radiation may have influenced the chemistry of early planetary systems, seeding the raw materials for complex molecules. And by observing how their light interacts with distant gas clouds, astronomers have mapped the universe's large-scale structure, revealing vast cosmic webs of matter invisible to telescopes. From potential harbingers of doom to tools for cosmic cartography, these bursts remind us that the universe's most violent phenomena often hold the keys to its deepest mysteries. Every galaxy spins like a cosmic carousel, with stars orbiting at speeds that should fling them into the void, yet something unseen holds them in place. This invisible scaffold, making up 85% of the universe's matter, is dark matter, an enigma that refuses to reveal itself except through gravity's ghostly tug. Imagine reaching out to steady a wobbling plate only to realize your hand is missing. That's the frustration astronomers face. We see dark matter's grip everywhere but can't grasp what it is. The smoking gun came in 2006 with the Bullet cluster, two galaxy clusters colliding 3.8 billion light-years away. X-ray telescopes revealed ordinary matter, hot gas, slowing like cars in a traffic jam, while gravitational lensing showed most of the mass had sailed right through unaffected. The verdict: dark matter doesn't interact with light or ordinary matter except through gravity. It's as if the universe is crowded with strangers who move your furniture but leave no fingerprints. Scientists have two leading suspects for this cosmic phantom: WIMP, weakly interacting massive particles, are hypothetical heavy particles that might linger from the Big Bang. Underground labs like Italy's Gran Sasso hunt them using vats of liquid xenon, waiting for a telltale flash when a WIMP bumps an atom. Then there are actions, particles trillions of times lighter than electrons, theorized to solve a quantum puzzle. If they exist, experiments like the Action Dark Matter experiment could catch them converting into microwaves in strong magnetic fields. Yet dark matter's fingerprints are everywhere. The cosmic microwave background, the afterglow of the Big Bang, shows its gravitational pull sculpted the early universe's structure. Computer simulations reveal galaxies couldn't form without its gravitational scaffolding. Even our Milky Way's rotation curve, how stars speed up or slow down at different distances, betrays the presence of an invisible halo 5 times more massive than all visible stars combined. The strangest twist: we might be swimming through a river of dark matter right now. Earth's orbit around the galaxy could create a wind of these particles. Some theories suggest dark matter could collect at Earth's core or even form exotic, dark stars. And while we've never directly detected it, its gravitational fingerprints are so undeniable that discovering its true nature could rewrite physics itself. From holding galaxies together to shaping the universe's large-scale structure, dark matter is the silent architect of the cosmos, an invisible hand we're only beginning to trace. If dark matter is the invisible glue holding galaxies together, dark energy is the shadowy force tearing the cosmos apart at its seams. Picture the universe as a loaf of raisin bread baking in an oven, except this oven keeps stretching the dough faster and faster, pushing every raisin farther from its neighbors. That's the chilling reality astronomers confirmed in 1998 when they discovered the expansion of the universe isn't slowing down as expected, it's accelerating. And whatever's causing this runaway effect, we've named it dark energy. The evidence came from studying distant supernovas, the cosmic mile markers we mentioned earlier. By measuring how fast these explosions were receding, two independent teams made the same shocking discovery. The universe's expansion rate is increasing over time, as if some anti-gravity force is pressing harder on the cosmic gas pedal. This revelation flipped cosmology upside down, earning the researchers the 2011 Nobel Prize in Physics. But here's the kicker: dark energy makes up 68% of the universe's total energy content, dwarfing both dark matter and ordinary matter combined. So what could this enigmatic force be? The leading candidate is Einstein's cosmological constant, an energy inherent to space itself. Imagine empty vacuum isn't truly empty but seething with quantum fluctuations that generate negative pressure, pushing space apart. The catch: quantum theory predicts this energy should be 120 orders of magnitude stronger than what we observe, a discrepancy so vast it's been called the worst theoretical prediction in physics history. The cosmic microwave background offers another clue. This ancient light from 380,000 years after the Big Bang shows tiny temperature variations that reveal how much dark energy existed in the infant universe. Combining this with galaxy surveys paints a bizarre picture. dark energy only became dominant about 5 billion years ago when the universe was already middle-aged. Before that, gravity's tug-of-war with initial expansion kept growth in check. Now, the million-dollar question: what's the universe's ultimate fate? If dark energy remains constant, we're headed for a big freeze, galaxies beyond our local group accelerating away until their light fades to black, leaving future astronomers with an empty sky. But if dark energy strengthens over time, the nightmare scenario unfolds: a big rip. First, galaxy clusters tear apart, then galaxies themselves, until even atoms are shredded in the final femtosecond. Recent measurements from the Dark Energy Survey suggest the truth may lie between these extremes, but with error bars still large enough to keep cosmologists awake at night. Perhaps most unsettling is realizing how little we understand about 95% of reality. While dark matter pulls, dark energy pushes, two invisible titans locked in a cosmic tug-of-war with the fate of everything hanging in the balance. And just like dark matter, we've never directly detected dark energy. We only see its fingerprints on the stretching fabric of spacetime. Some theories even suggest dark energy might be a fifth fundamental force, or evidence we're living in a multiverse where bubbles of space inflate eternally. What's certain is that solving this mystery could rewrite the laws of physics. Projects like the Vera Rubin Observatory and the Euclid Space Telescope are mapping billions of galaxies to trace dark energy's influence through cosmic time. They might reveal whether this force has changed over the eons, or if it's preparing to flip the universe's evolution into uncharted territory. One thing's clear: in the grand cosmic story, dark energy is the unpredictable wildcard, a reminder that even our most fundamental assumptions about reality might be up for grabs. The dance begins gently, almost imperceptibly. Two galaxies separated by 2.5 million light-years slowly falling toward one another, drawn together by gravity's invisible thread. This isn't the violent smash-up you might imagine, but a slow-motion ballet spanning billions of years. The Andromeda Galaxy, our Milky Way's nearest spiral neighbor, is hurtling toward us at 250,000 miles per hour. In about 4 billion years, these cosmic titans will embrace, merging into a single, colossal galaxy. Yet despite the scale of this collision, the stars within them won't crash like billiard balls. Space is so vast that stellar collisions are almost unheard of. Instead, gravity will sculpt both galaxies into something entirely new. Picture the Milky Way's familiar spiral arms, those bright streaks of stars and dust stretching across the night sky. As Andromeda approaches, its gravitational pull will warp these arms into long, shimmering tidal tails, streamers of stars flung outward like cosmic taffy. Computer simulations show the galaxies passing through each other multiple times, each close encounter stretching and twisting their structures until their original forms become unrecognizable. Stars will be tossed into new orbits, some ejected into intergalactic space, while others settle into a chaotic yet stable new arrangement. The process resembles two crowds of people walking through one another. Individuals change direction but rarely collide. What's truly astonishing is how little destruction occurs. Even when galaxies merge, the average distance between stars remains so vast, about 5 light-years in our galactic neighborhood, that direct collisions are nearly impossible. Our solar system might be flung farther from the galactic core, or even tossed into one of those glittering tidal tails, but the odds of our sun hitting another star are less than 1 in a trillion. The real drama unfolds not in stellar crashes, but in the interstellar gas and dust. These clouds, far denser than the space between stars, do collide, triggering bursts of star formation. When the antennae galaxies merged 500 million years ago, their gas clouds compressed, igniting a fireworks show of newborn stars visible across the universe. The aftermath of such mergers holds clues to the universe's most mysterious structures. Elliptical galaxies, those featureless, football-shaped collections of ancient stars, are thought to be the end products of spiral galaxy collisions. Over time, the merged galaxies' angular momentum smooths their structure into a more uniform shape, while their gas, used up in frenzied star formation, leaves them unable to birth new stars. The Milky Way and Andromeda will likely become a single, massive elliptical galaxy astronomers have nicknamed Milkdromeda, its golden glow dominated by aging stars. But galaxies don't just merge, they cannibalize. Our own Milky Way has absorbed smaller galaxies throughout its history, evidenced by streams of stars like the Sagittarius dwarf spheroidal, currently being torn apart by our galaxy's gravity. The Gaia Space Telescope has mapped these stellar rivers in exquisite detail, revealing ghostly remnants of past collisions. Even as we prepare for our cosmic merger with Andromeda, the Milky Way continues to consume smaller neighbors, growing like a celestial snowball. These collisions aren't just spectacular events, they're cosmic recycling programs. Each merger redistributes heavy elements forged in stellar furnaces, seeding future generations of stars and planets with the building blocks for rocky worlds and perhaps life itself. When we look at the violence of galaxy collisions in distant clusters, we're witnessing the engine of cosmic evolution, gravity weaving chaos into new order, ensuring the universe never remains static. So while the Milky Way's fate is sealed, the dance that follows will be anything but predictable, a slow, majestic reshuffling of starlight that will leave future night skies utterly transformed. Deep in the cosmic archives, astronomers have found what might be the universe's most terrifying energy converters, quasars. These brilliant beacons, first mistaken for nearby stars in the 1950s, are actually the hyperactive hearts of ancient galaxies, powered by supermassive black holes feeding on unimaginable quantities of gas. A single quasar can outshine 1,000 Milky Ways, blazing with the fury of an entire galaxy compressed into a region no larger than our solar system. Take quasar 3C273, for instance, one of the first ever discovered. Despite being 2.4 billion light-years away, it appears as the brightest radio source in its constellation. Yet what we're seeing is just the tip of the cosmic iceberg. As matter spirals toward the central black hole at nearly light speed, friction heats it to millions of degrees, creating a swirling disk of plasma so luminous it can be seen across the observable universe. Some quasars, like the record-breaking J0319-1720, pump out enough energy every second to power human civilization for 1 trillion years. These cosmic monsters didn't just dominate the early universe, they shaped it. The most distant quasar known, J134+0924, flickered to life just 670 million years after the Big Bang, when the cosmos was barely 5% of its current age. Its existence poses a staggering puzzle. How could a black hole with over 1 billion solar masses form so quickly? Current theories suggest these behemoths grew from rare, dense gas clouds in the early universe or were born from the direct collapse of supermassive stars, objects so massive they make today's largest stars look like specks of dust. Quasars also serve as cosmic lighthouses. Their light, traveling for billions of years, passes through intergalactic gas clouds, imprinting chemical signatures that reveal the universe's composition at different epochs. Without quasars, we'd have far fewer clues about how the first heavy elements spread through space, or when the cosmic fog of hydrogen atoms finally cleared during the epoch of reionization. Some even think quasars helped end the so-called cosmic dark ages, their intense radiation blasting away the hydrogen haze that once filled space. Yet there's an eerie twist to their brilliance. Every quasar we see is effectively a fossil, a snapshot of a black hole's meal from an era when galaxies were gas-rich and chaotic. Most nearby quasars have gone quiet as their fuel supplies dwindled, leaving behind dormant giants like Sagittarius, a star. But occasionally, we catch a galaxy waking its sleeping monster. In 2015, astronomers watched in real time as a previously quiet black hole in galaxy SJ 135+5117 suddenly began feasting, its brightness increasing 50-fold in just months, a reminder that even today, the universe can still summon these ancient terrors. What makes quasars truly indispensable is their dual nature, both destroyers and enablers. Their black holes may regulate galaxy growth by heating or ejecting gas that would otherwise form stars. Yet the same violent processes that power quasars likely seeded the universe with heavy elements essential for life. They are cosmic paradoxes, engines of annihilation that illuminated the path to our existence. As we study their light, we're not just observing distant objects, we're decoding the violent adolescence of the cosmos itself, one brilliant burst at a time. Less than a trillionth of a second after the Big Bang, something extraordinary happened. The universe exploded outward faster than the speed of light itself. Not just a gentle expansion, but an exponential stretching that inflated a subatomic speck of space to the size of a grapefruit in a fraction of a blink. This was cosmic inflation, a runaway expansion that set the stage for everything we see today, and solved two of cosmology's greatest puzzles in the process. First, the horizon problem. Look at the cosmic microwave background in opposite directions, and you'll find nearly identical temperature patterns. But these regions were too far apart for light or heat to have ever mixed in the universe's infancy. It's like finding identical snowflakes on opposite sides of the planet before clouds could spread moisture. Inflation fixes this by suggesting these areas were once neighbors, pressed together before the sudden stretching pulled them apart faster than information could travel. Then there's the flatness problem. Measurements show the universe's geometry is perfectly balanced between open and close, like a sheet of paper stretched so large its curvature vanishes. Without inflation, maintaining this balance over 14 billion years would require impossibly precise fine-tuning. But inflation's violent expansion would have flattened spacetime's wrinkles like smoothing a crumpled sheet by stretching it to cosmic proportions. The smoking gun for inflation, primordial gravitational waves, ripples in spacetime from inflation's quantum fluctuations, imprinted on the cosmic microwave background like fingerprints on glass. In 2014, the Bicep 2 team thought they'd spotted these waves in polarized light patterns, though dust interference later clouded the result. Yet the hunt continues, with next-generation telescopes like the Simons Array scanning for the telltale swirls that would confirm inflation's quantum origins. What powered this explosive growth? Theorists point to the inflaton field, a cosmic energy field that temporarily made gravity repulsive. As this field decayed, its energy transformed into the hot plasma of the Big Bang. Some models suggest inflation never truly ended, that our universe is just one bubble in an eternally inflating multiverse, where new universes sprout endlessly like buds on a fractal tree. From solving fundamental puzzles to potentially revealing multiple universes, cosmic inflation reshaped our understanding of reality's first moments. It's the ultimate plot twist, the realization that the universe's entire structure might hinge on a fleeting epoch when spacetime itself lost all sense of proportion. And if those primordial gravitational waves are ever confirmed, we'll have front-row seats to the very first chapter of existence. Somewhere in the universe, a single quantum event could trigger a catastrophe so absolute it rewrites the laws of physics from the ground up, not with a bang but with a whisper. This is vacuum decay, the universe's most insidious doomsday scenario, where a bubble of true vacuum expands at light speed, erasing everything we know about reality in its wake. And the terrifying part, it might already be happening, racing toward us from some distant galaxy, undetectable until it's too late. The nightmare hinges on the Higgs field, the invisible quantum molasses that gives particles their mass. While we perceive this field as stable, calculations suggest it might be metastable, like a marble balanced precariously on a hill. Right now, our universe sits in a false vacuum, a seemingly stable state that could at any moment tunnel into a lower energy true vacuum. If that happens in one tiny corner of space, the new ground state would spread outward in an unstoppable sphere, rewriting fundamental constants as it goes. Electromagnetism, gravity, even the nuclear forces, everything would reconfigure instantly. Atoms might dissolve, stars wink out, and the very fabric of chemistry could unravel before the light from the disaster even reaches our telescopes. The math behind this scenario comes from combining quantum field theory with cosmology. When physicists calculated the Higgs field's potential energy landscape, they found our current state isn't at the absolute bottom, it's sitting in a higher energy local minimum. Quantum fluctuations could theoretically knock it into the true minimum, releasing enough energy to rewrite spacetime itself. Estimates suggest the bubble wall would expand at nearly light speed, leaving no warning for civilizations in its path. One moment you're sipping coffee, the next your atoms cease to interact as they did moments before. But before you panic, here's the silver lining. If vacuum decay were likely, it probably would have happened already. The universe has existed for 13.8 billion years without resetting its physical laws. Calculations suggest the average time for such an event exceeds the current age of the universe by many orders of magnitude. Some theories even propose that the Higgs field might be more stable than we think, that our measurements of the top quark's mass could push the metastability threshold beyond practical concern. What's truly mind-bending is how vacuum decay reveals the fragility of our cosmic order. The constants we consider immutable might just be temporary configurations, frozen in place like ice on a pond that could liquefy without warning. It's a humbling reminder that for all our scientific progress, we're still deciphering the rulebook of existence, and some pages might yet contain universe-altering fine print. Experiments at the Large Hadron Collider continue refining our understanding of the Higgs field stability. Every new measurement of particle masses or coupling strengths tweaks the probability, like adjusting the tilt on that metaphorical hill. And while the odds seem vanishingly small, vacuum decay remains the ultimate check on cosmic hubris, proof that the universe might always hold one final surprise lurking in the quantum shadows. The sun seems steady from our vantage point, a reliable golden disk rising each morning. But peel back that calm facade, and you'll find a seething ball of plasma capable of tantrums so violent they can reach across 93 million miles and slap our civilization sideways. Solar flares are the sun's explosive outbursts, eruptions of energy equivalent to 1 billion hydrogen bombs detonating simultaneously. And when one of these electromagnetic hurricanes points directly at Earth, the consequences can be catastrophic. Take the Carrington event of 1859, the solar superstorm that serves as a warning from history. Astronomer Richard Carrington observed a blinding white solar flare through his telescope, followed 17 hours later by auroras so bright they turned night into day as far south as Cuba. Telegraph systems, the cutting-edge technology of the era, went haywire. Operators reported sparks leaping from equipment, some even sending messages with batteries disconnected, powered purely by geomagnetic currents. If a storm of that magnitude struck today, the damage would be measured in trillions. Modern infrastructure is far more vulnerable to space weather than 19th-century telegraph wires. A severe solar flare could induce ground currents strong enough to melt power grid transformers, massive machines that take years to replace. The Quebec blackout of 1989 offers a taste of this vulnerability, when a geomagnetic storm caused by a solar flare collapsed Canada's power grid in 90 seconds, leaving millions in the dark. But the Carrington-class event scientists worry about could knock out grids across continents, triggering cascading failures that might take months or years to repair. Satellites are equally at risk. Solar flares bombard Earth's atmosphere with X-rays and ultraviolet radiation, causing it to swell like a balloon. This expansion increases drag on low-orbiting satellites, potentially knocking them off course or even dragging them out of orbit prematurely. Meanwhile, high-energy protons from subsequent coronal mass ejections can penetrate spacecraft shielding, frying sensitive electronics. In 2003, a solar storm damaged Japan's Adios 2 satellite, killing its ability to communicate with Earth, a $500 million asset reduced to space junk in moments. The real nightmare scenario involves our digital backbone. Solar storms create geomagnetic fluctuations that can induce currents in undersea internet cables, potentially disrupting global communications. Researchers estimate a Carrington-level event could knock out up to 40% of internet infrastructure for weeks, with repair ships struggling to access damaged cables amid ongoing solar radiation. Unlike localized disasters, this would be a global crisis simultaneously crippling financial markets, supply chains, and emergency response systems without a single cloud in the sky. Yet there's hope on the horizon. NASA Parker Solar Probe is diving closer to the Sun than any spacecraft before, studying flare triggers deep in the corona. Early warning systems like the Discover satellite give utility operators about 30 minutes to isolate vulnerable grid components before a storm hits. And some nations, like the UK, have begun hardening critical transformers with protective circuitry. Still, with the Sun's activity ramping up toward its 11-year cycle peak in 2025, the clock is ticking. Solar flares remind us that we're not just inhabitants of Earth, we're citizens of a solar system, subject to the whims of a star whose moods can reach out and touch us across the void. From telegraph operators in 1859 to astronauts on the International Space Station today, humanity keeps learning the same lesson: respect the Sun's power or risk getting burned by forces older than life itself. Imagine a star ripped from its home galaxy and hurled into the abyss at speeds surpassing 1,000,000 miles per hour, so fast it could cross the distance from Earth to the Moon in just 11 minutes. These aren't science fiction, they're hypervelocity stars, cosmic fugitives ejected by one of the universe's most violent processes, the gravitational slingshot of a supermassive black hole. The runaway star He 0437-5439 epitomizes this phenomenon, streaking through intergalactic space at 2.5 million miles per hour, leaving behind a shimmering wake of shocked gas like the bow wave of a celestial speedboat. The physics behind these stellar projectiles is as elegant as it is brutal. When a binary star system drifts too close to a galaxy's central black hole, tidal forces rip the pair apart. One star gets captured into a frantic orbit, while its companion is flung outward at velocities that defy intuition, a gravitational assist so powerful it mimics the mechanics of a particle accelerator. The Milky Way's own supermassive black hole, Sagittarius, a star, has likely ejected dozens of these hypervelocity stars over its lifetime. One of them, S5-HVS1, was discovered racing outward at 3.7 million miles per hour, destined to escape our galaxy entirely and wander the void between galaxies indefinitely. What makes hypervelocity stars so fascinating isn't just their speed, it's the forensic clues they carry. The shocked gas trails they leave behind, glowing in X-rays and ultraviolet, act like cosmic breadcrumbs revealing their origins. He 0437-5439's trail, for example, suggests it was ejected from the Large Magellanic Cloud, a satellite galaxy of the Milky Way, by a black hole we didn't even know existed until its victim betrayed its presence. These stars also serve as probes of dark matter distribution. By tracking their trajectories backward, astronomers can map the gravitational fields they've traversed, exposing hidden mass in galactic halos. Yet not all hypervelocity stars come from black hole encounters. Some are survivors of supernovas in binary systems. When one star explodes, the sudden loss of mass can send its companion rocketing away like a champagne cork. Others might be relics of dwarf galaxies torn apart during galactic collisions, their stars flung into the void like debris from a car wreck. The diversity of their origins makes each hypervelocity star a unique time capsule, carrying chemical signatures that reveal the environment where it was born billions of years ago. Among the most intriguing is LP40-366, a massive O-type star barreling through space at over 1.6 million miles per hour. Its extreme speed and youth, just a few million years old, suggest it was born near the galactic center and violently expelled before it could settle into a stable orbit. Stars like this challenge our understanding of stellar nurseries, proving that even the densest star-forming regions can be disrupted by gravitational chaos. The ultimate fate of these cosmic outcasts is poetic. Unlike stars bound to galaxies, hypervelocity stars are condemned to eternal exile, their light gradually dimming as they drift into the freezing emptiness between galaxy clusters. Yet their loneliness serves a purpose. By studying their trajectories, astronomers can reconstruct the gravitational history of our local universe, tracing the invisible scaffolding that shapes everything we see. So the next time you gaze at the night sky, remember, somewhere out there, a rogue star is fleeing its birthplace at unimaginable speed, carrying secrets of the cosmos in its blazing heart. Galactic winds are the universe's ultimate eviction. Notices cosmic hurricanes of gas and radiation streaming from galaxies at thousands of miles per second, driven by the combined fury of supernovas and black holes. These aren't gentle breezes, but titanic outflows capable of stripping galaxies of their star-forming fuel, altering their destiny forever. Take the Perseus cluster, 19 million light-years away, where astronomers have witnessed winds so powerful they've sculpted colossal cavities in the hot gas surrounding galaxies' voids spanning hundreds of thousands of light-years, like bubbles blown in cosmic syrup. At the heart of this phenomenon lies a feedback loop of destruction and creation. When massive stars explode as supernovas, their shockwaves heat surrounding gas to millions of degrees, launching it into intergalactic space like steam from a pressure cooker. But the real architects are supermassive black holes. As matter spirals into these gravitational monsters, not everything crosses the event horizon. Some gets funneled into jets and outflows along the black hole's rotation axis, accelerated to nearly light speed by magnetic fields twisted into cosmic particle accelerators. The galaxy NGC 1275 provides a stunning example. Its central black hole has blasted out two symmetrical jets extending over 80,000 light-years, visible in radio waves as colossal lobes of energized particles. What makes these winds so consequential is their ability to regulate star birth. A galaxy's cold molecular gas is the raw material for new stars, but when galactic winds sweep through, they heat or eject this gas like leaves in a storm. In the Perseus cluster, X-ray telescopes have revealed vast regions where the gas has been pushed out entirely, leaving behind eerie quiet zones where stars can no longer form. It's a cosmic case of galactic starvation, with some simulations suggesting winds can remove up to 90% of a galaxy's star-forming fuel over time. The sheer scale is staggering. Some galactic winds, like those in the nearby starburst galaxy Messier 82, extend over 30,000 light-years, 3 times the diameter of our Milky Way, and contain enough gas to forge millions of stars. But instead of nurturing stellar nurseries, these winds become intergalactic pollution, enriching the space between galaxies with heavy elements forged in supernova explosions. This recycled material eventually becomes part of new galactic structures, linking generations of galaxies in an endless cycle of death and rebirth. Perhaps most fascinating is how these winds shape galactic evolution. Without them, galaxies would burn through their gas too quickly, becoming overcrowded stellar metropolises. But with too strong a wind, they'd expel all their gas and fade into darkness. The balance between outflow and retention determines whether a galaxy becomes a spiral like the Milky Way or a red and dead elliptical devoid of young stars. Even our own galaxy shows signs of past outflows, chimneys of hot gas stretching above and below the disk, evidence that galactic winds have touched us too. From sculpting galaxy clusters to seeding the cosmos with elements for future planets, these invisible rivers of energy are proof that even in the vastness of space, nothing exists in isolation. A star's death in one corner of the universe can trigger a chain reaction that echoes for billions of years, shaping galaxies far beyond its own. So the next time you gaze at a spiral galaxy's delicate arms, remember, its beauty was forged in the furnace of chaos, where winds blow not just across worlds but between them. Trillions of ghostly particles are passing through your body this very second, leaving no trace. Neutrinos, the universe's most elusive messengers, born in the hearts of exploding stars and colliding neutron stars, these nearly massless particles travel at near light speed, unaffected by magnetic fields or matter. When a supernova detonates, 99% of its energy escapes as neutrinos, a silent shout carrying secrets of the explosion's inner workings, long before light reaches us. Detecting these cosmic ghosts requires extraordinary ingenuity. Take supernova 1987A, the closest stellar explosion in 4 centuries. 3 hours before visible light arrived, neutrino observatories caught 24 particles, a whisper from the dying star's core. That handful of detections, gathered by tanks of cleaning fluid deep underground, confirmed theories about supernova mechanics and proved neutrinos move slightly slower than light. Today's detectors are far more sensitive. Japan's Super Kamiokan, a 40,000-ton water tank lined with light sensors, waits for the rare neutrino that interacts with matter, producing a telltale blue flash called Cherenkov radiation. But the real neutrino fireworks happen when neutron stars merge. The 2017 collision detected by LIGO also unleashed a neutrino burst caught by the ice cube detector at the South Pole. Buried in a cubic kilometer of Antarctic ice, ice cube's sensors track neutrinos that occasionally collide with ice molecules, creating secondary particles that streak through the ice like underwater fireflies. These events are cosmic treasure maps pointing back to the most violent phenomena in the universe. What makes neutrinos indispensable is their ability to escape where light cannot. While photons get trapped in a supernova's dense inner layers for hours, neutrinos zip straight out, giving astronomers a real-time look at stellar collapse. They're also chameleons, oscillating between 3 flavors: electron, muon, and tau, as they travel. This behavior, discovered by studying neutrinos from the Sun, proved the standard model of physics was incomplete, forcing scientists to revise their understanding of fundamental particles. The next frontier, neutrinos from the universe's birth. The relic neutrino background, a faint echo of the Big Bang, could reveal conditions in the first second of cosmic time if we can ever detect them. Projects like the Deep Underground Neutrino Experiment are pushing detection limits, while proposed space-based observatories aim to catch ultra-high-energy neutrinos from active galactic nuclei. These faint signals, carrying unfiltered stories from the cosmic depths, remind us that sometimes the universe's loudest secrets come in the quietest packages. For over a century, Einstein's theory of relativity predicted them, ripples in the fabric of spacetime, stretching and squeezing the cosmos like waves on an invisible ocean. But it took until September 14, 2015, for humanity to finally catch one. That's when the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves from 2 black holes spiraling into each other 1.3 billion light-years away. The signal lasted just 0.2 of a second, but in that blink of cosmic time, astronomy changed forever. Picture this collision: 2 black holes, each about 30 times the mass of our Sun, whirling around each other hundreds of times per second before merging into a single, more massive hole. The violence of that impact radiated outward in gravitational waves, carrying energy equivalent to 3 solar masses converted pure energy, a burst so powerful it briefly outshone all the stars in the observable universe combined. By the time these ripples reached Earth, they'd weakened to near nothingness, distorting LIGO 4-kilometer-long laser arms by less than 1,000th the width of a proton. That we detected this whisper at all is one of science's greatest triumphs. How does LIGO pull off such impossible sensitivity? Imagine splitting a laser beam down 2 perpendicular tunnels, bouncing the light off mirrors and recombining it. When gravitational waves pass through, they stretch one tunnel while squeezing the other, creating tiny mismatches in the laser light's return time. The system's so precise it can measure movements 10,000 times smaller than an atomic nucleus. But nature throws curveballs, earthquakes, trucks rumbling miles away. Even clouds drifting overhead can mimic gravitational waves. That's why LIGO has twin detectors in Louisiana and Washington, separated by 3,000 kilometers. Only signals appearing in both locations within light travel time get flagged as real. Since that first detection, LIGO and its European counterpart Virgo have opened a new era of multi-messenger astronomy. In 2017, they spotted 2 neutron stars colliding, an event that also flared in gamma rays, X-rays, and visible light. Telescopes worldwide swiveled to observe the aftermath, capturing the first ever images of heavy elements like gold and platinum being forged in real time. This single event confirmed decades of theories about the cosmic origins of precious metals and gave astronomers an unprecedented look at how gravity and light tell complementary stories. Gravitational waves also let us hear the universe in ways light never could. Black hole mergers are completely dark in electromagnetic radiation, but their gravitational waves reveal intricate details, masses, spins, even their final frenzied orbits before merging. Some collisions, like the record-breaking GW 190521 detected in 2019, produce black holes so massive they defy conventional stellar evolution theories. Others, like GW 190854, hint at exotic objects that might not fit neatly into our categories of neutron stars or black holes at all. The future promises even wilder discoveries. The upcoming LISA mission will place gravitational wave detectors in space, free from Earth's noise, to catch lower frequency signals, like the mergers of supermassive black holes in galactic cores. Pulsar timing arrays are listening for the gravitational wave background, the cumulative hum of all merging black holes across cosmic time. And who knows what surprises lurk in unexplored frequency bands, from revealing hidden populations of black holes to testing relativity in extreme conditions. Gravitational waves have given us front-row seats to the universe's most violent ballets, proving that even empty space itself can sing. Every second, Earth is bombarded by invisible bullets from deep space cosmic rays, atomic nuclei hurled across the galaxy at nearly light speed. Most come from supernova shockwaves, their remnants acting as natural particle accelerators far more powerful than anything we've built. But occasionally, we catch something inexplicable like the oh my god particle detected in 1991, a single proton with the kinetic energy of a baseball pitch packed into a subatomic speck. These aren't just scientific curiosities, they shape our world in surprising ways. When high-energy cosmic rays collide with Earth's upper atmosphere, they trigger cascades of secondary particles called air showers. Some of these collisions produce muons, heavy cousins of electrons, that penetrate deep underground, occasionally disrupting microchip operations in a phenomenon called single-event upset. In 2003, a cosmic ray-induced error caused a voting machine in Belgium to add 4,000 extra votes to a candidate's tally, proving even democracy isn't safe from interstellar interference. The real mystery lies with ultra-high-energy cosmic rays, particles so energetic they shouldn't exist. According to special relativity, protons traveling near light speed should interact with cosmic microwave background photons, losing energy over long distances, a limit called the Greisen-Zatsepin-Kuzmin cutoff. Yet the oh my god particle, with its 50-joule energy equivalent to a falling brick, smashed through this theoretical barrier. Its origin remains unknown, though some speculate it came from an active galactic nucleus, where jets from supermassive black holes could accelerate particles to impossible velocities. Modern detectors like the Pierre Auger Observatory in Argentina use square miles of water tanks to catch these rare events. When a cosmic ray strikes the atmosphere, the resulting particle shower creates ultraviolet flashes detectable by photomultiplier tubes. The observatory's findings suggest these ultra-high-energy rays might originate in nearby starburst galaxies, where frantic star formation creates ideal particle acceleration conditions. Other candidates include gamma-ray bursts or even exotic physics like decaying supermassive dark matter particles. Cosmic rays also play an unexpected role in cloud formation. The cloud experiment at CERN showed that ionization trails from cosmic rays can seed atmospheric aerosols, tiny particles around which water droplets form. This suggests a fascinating link between galactic astrophysics and Earth's climate, where distant supernovas might indirectly influence weather patterns by altering cloud cover. It's a humbling reminder that we're not just observers of the cosmos, but participants in an intricate interstellar dance. While most cosmic rays are blocked by our atmosphere, astronauts face serious exposure risks. A trip to Mars could subject travelers to radiation doses equivalent to one whole body CT scan per week, enough to increase lifetime cancer risks significantly. NASA Curiosity rover measured this firsthand during its cruise phase, detecting cosmic rays that would have penetrated any conceivable spacecraft shielding. Solutions being explored include magnetic deflectors or water-rich shielding materials, but the problem underscores how space travel remains tethered to Earth's protective bubble. From voting machine glitches to Martian mission risks, cosmic rays prove that the universe never lets us forget we're floating in a shooting gallery of high-energy particles. Their study bridges particle physics and astronomy, offering clues about galactic magnetic fields, dark matter, and the limits of Einstein's relativity. And every time we detect another oh my god particle, we're reminded how much we still don't know about the invisible bullets whizzing through space and through us every moment of our lives. Most planets orbit stars tethered by gravity like children holding onto a parent's hand. But the universe has its runaways, rogue planets, drifting through the interstellar void without suns to warm them. These cosmic nomads may outnumber stars in our galaxy by a staggering margin, yet they're nearly invisible to conventional telescopes. Some could even harbor vast subsurface oceans, kept liquid by tidal forces or radioactive decay, making them unexpected candidates for life in the coldest reaches of space. The first clue to their existence came from gravitational microlensing, a phenomenon where a rogue planet's gravity briefly bends and magnifies the light of a distant star as it passes in front. It's like spotting a pebble on a dark road by the way it distorts the glow of a street lamp far behind it. In 2011, astronomers detected a rogue planet roughly 6 times Jupiter's mass floating freely near the galactic center. Since then, surveys like OGLE and MOA have revealed dozens more, some likely ejected from their home systems during chaotic planetary migrations, others perhaps formed in isolation from collapsing gas clouds, never knowing the warmth of a star. The real intrigue lies in the possibility of subterranean oceans. Take a rogue planet with a thick ice shell, like a cosmic version of Jupiter's moon Europa. Internal heat from radioactive elements or gravitational flexing could maintain vast liquid water layers beneath the frozen surface. In our own solar system, hydrothermal vents on Earth's ocean floors thrive without sunlight, powered by chemical energy. Could similar ecosystems exist in the eternal night of a rogue planet's hidden sea? Some models suggest tidal forces from a moon or even the planet's own shifting crust might provide enough energy to sustain microbial life for billions of years. Then there's the mind-bending scenario of a rogue planet with an atmosphere. A thick hydrogen envelope could trap geothermal heat, creating surface temperatures above freezing, effectively turning a drifting world into a sealed greenhouse. French astronomer Frédéric Pont speculates such planets might resemble Titan, with organic chemistry brewing in the dark, potentially even forming complex molecules without starlight to drive photosynthesis. The coldest ones challenge our definition of habitability. At just a few degrees above absolute zero, any liquid water would be buried under hundreds of miles of ice. Yet even here, exotic antifreeze compounds like ammonia or salts could lower water's freezing point, creating isolated briny pockets where extremophile organisms might cling to existence. What's astonishing is how common these orphans might be. Microlensing surveys hint there could be billions of rogue planets in the Milky Way alone, some ejected from their birth systems during planetary billiards, others born in failed stellar nurseries. The upcoming Nancy Grace Roman Space Telescope, set to launch in the late 2020s, could detect thousands more, including Earth-sized free floaters. From frozen desert worlds to subsurface abysses teeming with alien chemistry, rogue planets force us to rethink where life might take root. They're proof that the universe doesn't play by our expectations, that life, if it exists beyond Earth, could thrive in the unlikeliest corners, untethered from any star's glow. The next generation of telescopes might finally pull these dark wanderers into the light, revealing whether the galaxy's loneliest worlds are also its most surprising. If neutron stars are nature's most extreme physics experiments, magnetars are their unpredictable, volatile siblings, cosmic monsters wielding magnetic fields so strong they rewrite the rules of reality. Imagine a magnetic force a quadrillion times more powerful than Earth's, capable of twisting atomic structures into impossible shapes or erasing every hard drive on the planet from halfway across the galaxy. These aren't hypothetical scenarios. Magnetars exist, and their outbursts make supernovas look tame by comparison. Take the event that shook astronomers in December 2004. A magnetar named SGR 1806-20, 50,000 light-years away in the constellation Sagittarius, unleashed a starquake, a crust-shattering seismic shift on its surface. For 500 milliseconds, this eruption of energy outshone the full moon, despite originating from an object smaller than Manhattan. The blast compressed Earth's magnetosphere, distorting radio waves globally and triggering the first ever observed disturbance in our planet's magnetic field from a cosmic explosion. If this magnetar had been within 10 light-years, the radiation could have stripped our ozone layer, triggering a mass extinction. What fuels such mind-bending power? Magnetars are born from the ashes of supermassive stars that died with a twist, literally. When a massive star collapses, conservation of angular momentum spins its core faster, while convective currents amplify its magnetic field like a cosmic dynamo. The result is a neutron star spinning hundreds of times per second, its magnetic field lines so tightly wound they could snap like over-tensioned rubber bands. This energy doesn't just linger, it erupts periodically in gamma-ray flares and X-ray outbursts, making magnetars the universe's most volatile magnetic phenomena. The physics gets even stranger at the quantum level. In a magnetar's atmosphere, electrons can't even orbit atoms normally. The field is so intense it distorts their paths into elongated spirals. Protons and neutrons align like compass needles, creating a crystalline crust under unimaginable stress. When this crust fractures during a starquake, it releases pent-up magnetic energy equivalent to the sun's total output over 100,000 years in milliseconds. The 2019 detection of a magnetar flare from NGC 2535, 30 million light-years distant, proved these outbursts can be detected across intergalactic space. Yet magnetars aren't just agents of destruction. Their extreme environments test the limits of quantum electrodynamics, offering insights we could never glean from Earth-bound labs. Some theories suggest their magnetic fields might even catalyze exotic quantum phenomena, like the spontaneous creation of electron-positron pairs from pure vacuum. And because their magnetic fields decay over millennia, older magnetars might hold clues to the life cycle of neutron stars, eventually fading into quieter, but equally mysterious stellar remnants. The scarred survivors of stellar catastrophes, magnetars remind us that the universe reserves its most violent surprises for the smallest packages. From rewriting atomic behavior to threatening planetary atmospheres across light years, they prove that magnetic fields, when taken to extremes, can be as universe-shaping as gravity itself. And with new X-ray telescopes scanning the skies, we're just beginning to uncover how many of these magnetic monsters lurk in the cosmic dark, waiting to snap. Black holes devour everything in their path, but what if the universe has cosmic fountains to balance these drains? Enter white holes, the hypothetical opposites of black holes, where matter erupts outward instead of vanishing forever. While no white hole has ever been observed, their existence emerges from the same equations that predict black holes' Einstein's theory of general relativity. Flip a black hole's equations in time, and you get a white hole, a region of spacetime where nothing can enter, only escape. Imagine trying to paddle a boat toward a waterfall that violently repels you, hurling water outward with impossible force. That's the bizarre physics of a white hole. One compelling theory places white holes in the realm of loop quantum gravity, a framework attempting to reconcile relativity with quantum mechanics. Here, a collapsing black hole might rebound into a white hole at the quantum level like a compressed spring recoiling. The process would take billions of years for a stellar mass black hole, far longer than the current age of the universe, but for tiny primordial black holes formed in the Big Bang's chaos, this transformation could already be underway. If true, some gamma-ray bursts or fast radio bursts might actually be the death cries of ancient black holes turning inside out. Then there's the wormhole connection. Theoretical models suggest white holes could serve as the exit for an Einstein-Rosen bridge, a tunnel through space-time linking distant regions. While traversable wormholes remain speculative, the math hints that matter falling into a black hole might emerge from a white hole elsewhere. The catch: any realistic wormhole would likely collapse instantly under its own gravitational forces, unless propped open by exotic matter with negative energy, something we've never observed. The most tantalizing white hole candidate might have already been spotted. In 2006, astronomers detected an unusual gamma-ray burst, GRB 060614, with no associated supernova. Its light curve matched simulations of a white hole's explosive birth. Skeptics argue it was just an unusual supernova, but proponents note its symmetry and energy profile align eerily with theoretical predictions. Whether cosmic math fiction or hidden reality, white holes challenge our intuition about causality and time. They're a reminder that the universe's rulebook might have pages we've yet to turn, where endings become beginnings and destruction fuels creation. Until we catch one in the act, they remain one of cosmology's most provocative what-ifs, teasing us with the possibility that even spacetime has an emergency exit. Imagine crushing a beam of light into a space so tiny its own energy collapses into a black hole. No stars, no matter, just pure radiation squeezed into oblivion. This is the mind-bending concept of a Kugelblitz, German for ball lightning, a black hole born not from collapsing matter, but from the sheer concentration of energy itself. Einstein's equations make no distinction. Enough energy packed into a small enough volume will warp spacetime just like mass does. And in theory, if you could focus enough lasers or gamma rays into a single point, you could create a singularity out of light alone. The numbers are staggering. To form a quadrille blitz the mass of a small asteroid, you'd need to concentrate more energy than humanity has produced in its entire history into a space smaller than an atom. That's because energy and mass are two sides of the same coin, linked by Einstein's famous E equals mc squared. The Planck energy, the scale where quantum gravity effects dominate, becomes relevant here about 10 quadrillion times the energy of the Large Hadron Collider's most powerful collisions. Yet nature might have shortcuts. Some theories suggest ultra-high-energy cosmic ray collisions or gamma-ray bursts could, under freak conditions, momentarily create microscopic quadrille blitzes that evaporate instantly via Hawking radiation. Where this gets surreal is the sci-fi potential. A civilization advanced enough to harness such energies could, in principle, build quadrille blitzes as energy storage devices. Black hole batteries, where matter fed into the tiny singularity releases energy with near-perfect efficiency. Some speculative designs even propose using their Hawking radiation as propulsion for interstellar ships. The catch: containment. A 1-ton quadrille blitz would be about as wide as an atomic nucleus, yet radiate as much power as a nuclear reactor, requiring impossible precision to maintain. Then there's the ultimate twist: quadrille blitzes might already exist naturally. If the early universe had regions of extreme energy density, quantum fluctuations could have birthed primordial quadrille blitzes that either evaporated instantly or persist today as dark matter candidates. Experiments searching for Hawking radiation from microscopic black holes could, in theory, stumble upon evidence of these ghostly energy traps. From a theoretical curiosity to a potential engineering nightmare or miracle, quadrille blitzes stretch our understanding of energy and gravity to the breaking point. They're reminders that in Einstein's universe, even something as massless as light can wield the crushing weight of a black hole when squeezed tightly enough. And while we're centuries away from creating one intentionally, their possibility proves that physics still holds surprises wilder than fiction. Our galaxy isn't just drifting aimlessly through space, it's being pulled towards something colossal, a gravitational siren call we can't see. 650 million light-years away lies the Great Attractor, a mysterious concentration of mass so powerful it's tugging the Milky Way and thousands of other galaxies toward it at 14 million miles per hour. But here's the cosmic irony. We're trying to study a force that hides directly behind our own galactic backyard, obscured by the thick dust and stars of the Milky Way's disk, a region astronomers call the zone of avoidance. Imagine trying to spot a lighthouse through a fog bank while standing in another lighthouse's beam. That's the challenge scientists face. The Great Attractor's location in the constellation Norma places it directly behind the densest part of our galaxy's plane, where visible light gets absorbed by interstellar dust. It took X-ray and radio telescopes piercing through this cosmic veil to reveal hints of what's pulling us. The first breakthrough came in the 1980s when surveys showed thousands of galaxies all streaming toward the same invisible focal point, like metal filings drawn to a hidden magnet. What's truly staggering is the scale of this structure. The Great Attractor isn't just a massive galaxy cluster, it's the heart of the Laniakea supercluster, a cosmic web containing 100,000 galaxies spanning 500 million light-years. Picture a spider's silk threads with the Great Attractor as the central knot, and our Milky Way as one tiny speck clinging to a strand. This realization redefined our cosmic address. We're not just part of the Virgo supercluster, but a peripheral suburb of Laniakea, a Hawaiian term meaning immeasurable heaven. The latest research suggests the Great Attractor might not even be the final destination. There's something even larger beyond it, the Shapley supercluster, 850 million light-years away, which could be the true end point of this intergalactic conveyor belt. What makes this cosmic tug-of-war so fascinating is how it reshapes our understanding of gravity's reach. These flows of galaxies, stretching across hundreds of millions of light-years, reveal how mass structures sculpt the universe on the grandest scales, with galaxies acting like tracers in an invisible river of dark matter. From behind the zone of avoidance to the frontiers of supercluster mapping, the Great Attractor reminds us that even in our cosmic neighborhood, the universe still holds profound mysteries. Every breakthrough peels back another layer, showing us that what once seemed like random motion is actually part of an intricate gravitational symphony, one where dark matter conducts from the shadows and galaxies dance to rhythms we're only beginning to hear. Beneath the smooth canvas of spacetime we experience lies a hidden chaos, a seething quantum foam where reality itself churns like an endless storm at scales a million billion times smaller than an atom. This isn't poetic exaggeration, it's the bizarre prediction of quantum mechanics when pushed to its limits at the Planck length, roughly 10 to the minus 35 meters. Here, spacetime isn't the static stage Einstein imagined. It's a turbulent froth where microscopic black holes and wormholes flicker in and out of existence in intervals so brief they defy time as we know it. Think of it as the universe's version of static noise, but instead of distorting a radio signal, it distorts the very fabric of existence. The quantum foam concept emerged from physicist John Wheeler's work in the 1950s, blending quantum uncertainty with general relativity's warping of spacetime. At these unimaginably tiny scales, Heisenberg's uncertainty principle allows for wild energy fluctuations, particle-antiparticle pairs popping into existence like bubbles in a boiling pot, only to annihilate moments later. These aren't just mathematical abstractions. In experiments like the Casimir effect, we've glimpsed their shadowy influence. Two metal plates placed microscopically close in a vacuum experience an invisible force pushing them together, caused by quantum fluctuations between them being slightly different from those outside. What makes quantum foam so revolutionary is how it challenges our notions of continuity. We perceive spacetime as smooth because our senses, and even our finest instruments, average over these frenetic fluctuations, like how a fast-spinning wheel appears solid. But probe deep enough and the wheel reveals its spokes. Some theories suggest this foamy structure could explain why gravity resists unification with quantum mechanics. At Planck scales, spacetime's very geometry might become discrete, forcing us to rewrite physics from the ground up. The implications ripple outward. If spacetime isn't fundamental but emerges from something more basic like information or quantum entanglement, then black holes might not be eternal prisons. Information swallowed by a singularity could resurface encoded in the foam's fluctuations, offering a potential solution to Hawking's infamous information paradox. Even time itself might lose its arrow in this froth, with microscopic regions spontaneously flowing backward before blending into the larger forward march of entropy. Efforts to detect quantum foam's fingerprints are pushing technology to its limits. Gamma-ray telescopes search for subtle delays in high-energy photons traversing billions of light-years. If spacetime is foamy, shorter wavelength photons should stumble slightly more, like hikers navigating rocky terrain. Surprisingly, observations of distant quasars have found no such lag, hinting that spacetime might be smoother than predicted, or that our theories need refinement. Meanwhile, tabletop experiments using supercooled quantum oscillators aim to sense spacetime's granularity directly, hunting for telltale jitters in particles suspended in electromagnetic fields. From birthing alternate universes in fleeting bubbles to potentially holding the key to quantum gravity, the foam beneath reality's surface reminds us that the universe's true nature might be wilder than anything we've dared imagine. It's a frontier where the rules we take for granted dissolve into chaos, and where the next physics revolution might be bubbling up one Planck length at a time. The universe as we know it might be sitting on borrowed time, not from a cosmic collision or heat death, but from a quantum glitch so profound it could rewrite the laws of physics in an instant. This nightmare scenario hinges on the concept of the false vacuum, a precarious state where the fabric of reality isn't in its true, most stable configuration, but instead trapped in a temporary equilibrium like a marble resting on a ledge instead of rolling to the valley floor. And if quantum fluctuations ever knock that marble loose, the consequences would be unimaginable. Consider the Higgs field, the invisible energy field that gives particles their mass. What if this field isn't at its lowest possible energy state? Calculations suggest our universe might be in a metastable false vacuum, a cosmic illusion of stability. At any moment, in some distant corner of space, quantum tunneling could trigger a bubble of true vacuum to form. This bubble would expand at light speed, reshaping fundamental constants as it goes. Inside this wavefront, the strong nuclear force might vanish, atoms disintegrate, and the very rules of chemistry dissolve. The change would propagate so fast that no warning could reach civilizations in its path. One moment, stars shine as usual. The next, the universe's operating system reboots with entirely new parameters. The scariest part, we might already be in the bubble's path without knowing. If a true vacuum transition began a billion light years away, its light speed expansion would give us zero advance notice. Unlike asteroid impacts or solar flares, this existential threat offers no before or only an after we'd never lived to comprehend. Yet there's cold comfort in statistics. The probability of such an event occurring in our cosmic neighborhood is astronomically low, likely far exceeding the universe's current age. The Higgs field's metastability depends on precise measurements of particle masses, and recent data from the Large Hadron Collider hints our vacuum might be more stable than previously feared. But the false vacuum isn't just a doomsday hypothetical, it's a window into deeper mysteries. If multiple vacuum states exist, our universe might be one of countless bubbles in a multiverse foam, each with different physical laws. Some theories suggest cosmic inflation could have begun when a higher energy vacuum decayed into ours, sparking the Big Bang. This connects to wilder ideas, like the notion that black holes might nucleate new universes with tweaked physics in their interiors. What grounds all this speculation is the realization that our universe's apparent permanence might be an accident of timing. The fact that we're here to ponder it suggests the false vacuum, if it exists, is impressively long-lived. Future particle colliders could refine our understanding of the Higgs field stability, potentially ruling out the scenario entirely or confirming we're living on cosmic thin ice. Until then, the false vacuum stands as physics' most humbling thought experiment, a reminder that reality's foundations might be shakier than they appear, and that even the laws of nature could be temporary tenants in an ever-changing quantum landscape. From collapsing black holes to runaway hypervelocity stars, we've explored 23 of the universe's most astonishing forces, cosmic titans that sculpt galaxies, forge elements, and bend reality itself. Just imagine supernovas seeding space with stardust, quasars outshining entire galaxies, and invisible dark matter weaving the cosmic web that holds everything together. Yet, believe it or not, this barely scratches the surface. 7 even wilder phenomena still await in a potential Part 2, from time-bending tachyons to the universe-ending Big Rip. What's truly humbling is realizing how these forces intertwine. Magnetars don't just twist space-time, they illuminate how magnetic fields can rival gravity itself. Galactic winds don't merely strip galaxies of gas, they recycle heavy elements into future generations of stars and planets. Even quantum foam, the turbulent foundation of reality, connects to the birth of black holes and the fate of information itself. The universe operates like an infinite Rube Goldberg machine, where one cataclysmic event triggers another across billions of years. Now we want to hear from you. Which force left you awestruck? Was it the neutron stars with their incomprehensible density, or dark energy's silent push accelerating the cosmos toward an uncertain fate? Drop your favorites in the comments and tell us which of the remaining 7 you're dying to explore next. Should we dive into the holographic principle's radical reimagining of spacetime? Or unpack how cosmic strings might twist the universe like scars from the Big Bang? This cosmic journey doesn't end here. Every new telescope, particle detector, and space probe peels back another layer of the universe's grandeur, and your curiosity fuels the adventure. So hit subscribe to join us for part 2, where we'll confront forces that redefine existence itself. Until then, keep looking up and wondering what other unimaginable powers lurk in the cosmic dark. The universe has whispered 23 secrets, countless more await their turn.